Postfix notation, also called reverse Polish notation, RPN, writes an expression so that every operator follows all of its operands. For example, the infix expression 3 plus 4 becomes 3 4 plus in postfix. The main characteristics are: no parentheses are needed because the order of evaluation is completely encoded by the position of operators. The evaluation order is left to right using a last in first out LIFO rule, which matches the natural behavior of a stack. Each operator knows how many operands it needs arity. A binary operator consumes 2 operands, a unary operator consumes 1, etc. The notation is unambiguous. There is exactly one way to read an expression, unlike infix, where different parenthesizations can give the same string. A real-world analogy: think of a conveyor belt in a factory where workers' operands walk forward, and when a machine operator appears, it picks up the required number of workers from the end of the belt, processes them, and puts the result back onto the belt. Because the belt is a stack, the most recent workers are always the ones taken first. Explanation: to turn an ordinary infix expression, the way we usually write maths, into postfix, we use the shunting yard algorithm invented by Dijkstra. The algorithm keeps 2 structures, a stack for operators and a list for the output. It follows 2 rules: precedence, times and divided by bind tighter than plus and minus, and associativity. Most binary operators are left associative, exponentiation is right associative. Pseudocode: 1 for each token in the infix string. A if the token is an operand, number, variable, append to output. B if the token is a left parenthesis, push onto operator stack. C if the token is a right parenthesis, pop operators to output until left parenthesis is found, discard the left parenthesis. D if the token is an operator op1, while there is an operator op2 on the top of the stack, and either op1 is left associative and precedence of op1 is less than or equal to precedence of op2, or op1 is right associative and precedence of op1 is less than precedence of op2, pop op2 to output. Then push op1 onto the stack. 2. After the input ends, pop any remaining operators to output. Illustrative example: convert a plus b times c minus d divided by e. Read left parenthesis, push left parenthesis. Read A is output A. Read plus, push plus. Read B, output a B. Read right parenthesis, pop plus, output a B plus, pop left parenthesis. Read times, stack empty, push times. Read left parenthesis, push left parenthesis. Read C, output a B plus C. Read minus, push minus. Read D, output a B plus CD. Read right parenthesis, pop minus, output a B plus CD minus, pop left parenthesis. Read divided by, times on stack has same precedence and is left associative, so pop times, output a B plus CD minus times, then push divided by. Read E, output a B plus CD minus times E. End of input, pop divided by, final postfix, a B plus CD minus times E divided by. The resulting string can be evaluated without any parentheses. The algorithm mirrors a real-world stack of trays. You keep putting operators on top of the stack and only take them off when a higher priority operator arrives or a closing parenthesis tells you to finish the current group. Evaluating a postfix expression uses a single stack that holds intermediate results. The steps are: Step 1. Scan the expression token by token from left to right. Step 2. If the token is an operand, push its numeric value or variable value onto the stack. Step 3. If the token is an operator, pop the required number of operands, apply the operator and push the result back. Because the operator always appears after its operands, the stack always contains the correct arguments. Complete example: evaluate the classic expression 5 1 2 plus 4 times plus 3 minus, which equals 14. Token 5 push 5, stack now contains 5. Token 1 push 1, stack now contains 5 1. Token 2 push 2, stack now contains 5 1 2. Token plus pop 2 and 1 1 plus 2 equals 3 push 3, stack now contains 5 3. Token 4 push 4, stack now contains 5 3 4. Token times pop 4 and 3 3 times 4 equals 12 push 12, stack now contains 5 12. Token plus pop 12 and 5, 5 plus 12 equals 17, push 17. Stack now contains 17. Token 3 push 3, stack now contains 17, 3. Token minus pop 3 and 17, 17 minus 3 equals 14, push 14. Stack now contains 14. At the end, the stack holds a single value 14, which is the answer. The process is analogous to a chef preparing a dish. Ingredients or operands are placed on the counter, and each cooking step or operator takes the needed ingredients, mixes them, and returns a new ingredient for the next step. Real programs must cope with many kinds of operators and operand formats. Binary operators plus minus times divided by raised to need two operands. When the operator is encountered, we pop the right-hand operand first, then the left-hand operand, because the stack is last in first out. For exponentiation, we usually treat it as right associative during the conversion phase, but during evaluation it is just another binary operator. Result equals left raised to right. Unary operators like unary minus or logical not need only one operand. A common technique is to give the unary operator a distinct symbol, for example tilde for unary minus. During evaluation, we pop a single value, apply the unary operation, and push the result. Multi-digit numbers are read as a whole token before being pushed. In a string 1234 plus, the tokens are 12, 34, and plus. The lexer separates numbers by spaces or other delimiters, so the stack receives the integer values 12 and 34. Variables are treated like operands whose numeric value is looked up in a symbol table. Example: expression xy plus with a map x equals 7, y equals 3. When token x is read, we push 7. When y is read, we push 3, then plus produces 10. The evaluation loop can therefore be written in generic pseudocode. For each token, if the token is a number, push the numeric value of the token. Else, if the token is a variable, push the value from the environment for that variable. Else, if the token is a unary operator, pop a value, apply the unary operation to the value, and push the result. Else, if the token is a binary operator, pop the right operand, pop the left operand, apply the binary operation to left and right, and push the result. This design makes it easy to extend the language with new operators such as factorial exclamation mark by adding a case to the apply functions. The evaluation algorithm touches each token exactly once, performing a constant amount of work, push, pop, or a simple arithmetic operation for each token. Therefore, the running time is linear in the length of the expression, big O of n, where n is the number of tokens. The auxiliary data structure is the operand stack. In the worst case, when the expression consists of only operands before any operator appears, for example 1, 2, 3, 4, 5, and so on, the stack can grow to hold all n operands. Hence, the extra memory usage is also big O of n. No recursion or additional arrays are required, making the algorithm space efficient. In practical terms, the constants are tiny. Each push and pop is a big O of one array index operation, and the arithmetic work is the same as any normal calculation. This is why many calculators and programming language interpreters, for example Forth and PostScript, use postfix evaluation under the hood. A malformed postfix string can cause runtime errors or give a wrong result. The two most common problems are: insufficient operands. An operator appears when there are fewer than the required number of values on the stack. Example, 5 plus. When plus is read, we try to pop two numbers, but only one 5 is present. The evaluator should detect this condition and report error, not enough operands for plus at position x. Excess operands. After processing the whole expression, the stack contains more than one value. Example, 2, 3, 4 plus leaves the stack with values 2 and 7. This indicates that some operator is missing. The evaluator should report error, too many operands, expression did not reduce to a single result. Other validation checks include: unknown symbols, neither operand nor defined operator, report invalid token. Mismatched arity for a known operator. For example, using a binary operator as unary, report specific arity error. Implementation tip: during evaluation, keep a counter of stack size. Before applying a binary operator, ensure size greater than or equal to 2. Before a unary operator, ensure size greater than or equal to 1. After the loop, confirm that size equals 1. Raising an exception or returning an error code makes the calling program robust. These checks are similar to a quality control inspector on a production line. The inspector stops the line if a part is missing, not enough operands, or if extra parts are left over, too many operands, ensuring the final product is correct. Question 1. Trace the stack. Given the postfix expression 832 times plus 5 minus, show the content of the operand stack after each token is processed and write the final result. Expected answer: a table like the one in the evaluation example, ending with stack equals 9. Question 2. Write conversion code. Write a short function in C++, Java, or Python that implements the shunting yard algorithm for the operators plus, minus, times, divided by, and parentheses. The function should take a string containing a space-separated infix expression and return a space-separated postfix string. Scoring: correctness of precedence handling, use of stack, and handling of parentheses. Question 3. Combined conversion and evaluation. The expression a minus b raised to the power of c plus d divided by e is given, where the variable values are a equals 5, b equals 2, c equals 3, d equals 1, e equals 2. Part A. Convert the infix expression to postfix. Part B. Evaluate the postfix expression using the variable values. Show all intermediate steps for both parts. Expected answer: Part A b minus c d plus raised to the power of e divided by. Expected answer: Part B. Substitute numbers becomes 5 2 minus 3 1 plus raised to the power of 2 divided by, which evaluates to open parenthesis 5 minus 2 close parenthesis raised to the power of open parenthesis 3 plus 1 close parenthesis divided by 2 equals 3 to the power of 4 divided by 2 equals 81 divided by 2 equals 40.5. These questions force the student to visualize stack operations. Roman 2 implement the algorithm, and Roman 3 apply it to real values, covering the full learning objective.